You are listening to DynamoDB Pro, a developer's practical guide. Like and subscribe to keep up to date on our latest audiobooks. DynamoDB Pro, a developer's practical guide. Welcome to the world of NoSQL and DynamoDB. For decades, the world of data storage was largely dominated by a single paradigm: relational databases, often referred to by their structured query language, SQL. Think of them as meticulously organized filing cabinets, where every piece of paper or record has a predefined form and all the information fits neatly within rows and columns, linked together by precise relationships. This approach brought order, consistency, and powerful querying capabilities, making them the backbone of countless enterprise applications, financial systems, and traditional websites. But as the digital landscape evolved, so too did the demands on our data systems. The advent of the internet, the explosion of mobile devices, and the need for applications to serve millions, sometimes billions, of users simultaneously exposed the limitations of this highly structured approach. Imagine our filing cabinet trying to handle not just thousands, but millions of new documents per second, each arriving in a slightly different format and needing to be retrieved in milliseconds by users across the globe. The traditional model, while robust, often struggled with the sheer scale, flexibility, and performance required by modern web-scale applications. This challenge gave rise to a new family of databases, collectively known as NoSQL, meaning not only SQL. NoSQL databases offered a different philosophy, prioritizing flexibility, massive scalability, and blazing fast performance for specific kinds of data access patterns over the strict adherence to relational models. They come in various flavors, each optimized for different needs. Some are like simple key-value stores, others handle documents, while others excel at graph-like relationships. They represent a fundamental shift in how we think about storing and retrieving information. Instead of starting with a rigid schema and trying to make our data fit, NoSQL often allows data to define its own structure, giving developers unparalleled agility. Within this diverse NoSQL ecosystem, one service stands out for its unique blend of attributes: Amazon DynamoDB. What is Amazon DynamoDB? Amazon DynamoDB is a fully managed, serverless, NoSQL database service offered by Amazon Web Services, or Oz. But what do these terms really mean for a developer? Fully managed. This is perhaps its most compelling feature. With DynamoDB, you don't have to worry about provisioning servers, installing software, patching operating systems, setting up replication, or handling backups. Oz takes care of all the underlying infrastructure and operational tasks. As a developer, your focus remains entirely on designing your data model and writing your application code, not on database administration. Serverless. This term implies remarkable operational simplicity and cost efficiency. DynamoDB scales its capacity up and down automatically to handle your application's workload, whether it's processing a handful of requests per second or millions. You pay only for the resources you actually consume or for the capacity you choose to provision without needing to over-provision for peak loads. NoSQL. As we discussed, DynamoDB fits into the NoSQL category, specifically functioning as a key-value and document database. This means it stores data in flexible, schemaless items, making it highly adaptable to evolving application requirements. The story of DynamoDB actually begins internally at Amazon. Before it was offered as a public service, Amazon faced immense challenges scaling its own e-commerce platform and other services using traditional relational databases. Their engineers pioneered the concepts foundational to DynamoDB, realizing they needed a database that could deliver consistent, single-digit millisecond response times at any scale. This experience shaped DynamoDB into the powerhouse it is today, capable of handling trillions of requests per day and supporting some of the world's most demanding applications. When does DynamoDB shine? Identifying its ideal use cases. While highly capable, DynamoDB isn't a one-size-fits-all solution. It excels in specific scenarios where its core strengths align perfectly with application requirements. Imagine building an application that needs to handle massive scale with predictable performance. Think of global gaming leaderboards, real-time bidding platforms, or user profile services for millions of daily active users. These systems require consistent, low-latency access to data, regardless of how much traffic they receive. DynamoDB is designed to maintain single-digit millisecond response times even as your data grows to petabytes and your traffic bursts to millions of requests per second. Support unpredictable, bursty workloads. E-commerce promotions, social media viral events, or IoT device data streams often lead to unpredictable spikes in traffic. DynamoDB's ability to automatically scale its capacity makes it an ideal choice for such volatile workloads, preventing performance bottlenecks without manual intervention. Manage flexible and evolving data. In agile development environments, data schemas often change. DynamoDB's schemaless nature allows you to add or modify attributes to items without migrating your entire database or affecting existing data, accelerating your development cycles. Serve as the backend for serverless applications. DynamoDB pairs exceptionally well with AWS Lambda functions, forming the core of highly scalable, cost-effective serverless architectures. This combination allows developers to build powerful applications without managing any servers. Store high-velocity IoT data. Sensors, devices, and connected cars generate continuous streams of data. DynamoDB's throughput capabilities make it perfect for ingesting, storing, and querying this real-time data. Power applications requiring high availability. Built-in replication across multiple AWS availability zones ensures your data is highly durable and available, automatically surviving outages in a single data center. Common types of applications where DynamoDB truly excels include user profiles and personalization, storing user data, preferences, and session information. Gaming, leaderboards, player data, game state. Ad tech, real-time bidding, user targeting data. E-commerce, shopping carts, product catalogs, order history. IoT, Internet of Things, device telemetry, sensor data. Media and entertainment. Content metadata, streaming session data. While DynamoDB is powerful, it's generally less suitable for applications heavily reliant on complex, multi-table joins or ad hoc analytical queries across large datasets. For those scenarios, a relational database or a data warehouse might be a better fit. But for core operational data that needs high performance and scalability, DynamoDB is often the superior choice. A glimpse under the hood, how DynamoDB works simply. So, how does DynamoDB achieve this incredible scale and performance? At a high level, it distributes your data across multiple storage units called partitions. When you store an item, DynamoDB figures out which partition it belongs to based on a special value called the partition key. This intelligent distribution allows DynamoDB to handle massive amounts of read and write traffic by parallelizing operations across these partitions. Let's quickly introduce the fundamental building blocks you'll interact with. Tables. These are similar to tables in a relational database, serving as logical groupings for your data. For instance, you might have a users table or an orders table. Items. An item is essentially a single record in your table, akin to a row in a relational database table. For example, a single user's profile would be an item in the users table. Attributes. These are the individual data elements that make up an item. Think of them as columns in a relational table, but with a lot more flexibility. An item might have attributes like username, email, creation date, or even complex nested structures like address or preferences. The beauty of DynamoDB's schemaless nature is that items within the same table don't have to have the exact same attributes. When you interact with DynamoDB, whether you're adding new data, retrieving existing information, or updating records, you'll be performing operations measured in terms of read capacity units, RCUs, and write capacity units, WCUs. These units represent the amount of throughput your table can sustain. Don't worry about the precise calculations just yet. For now, simply understand that DynamoDB has built-in mechanisms to ensure your application gets the capacity it needs when it needs it. You'll also encounter the concepts of eventual consistency and strong consistency. These refer to how quickly changes to your data are propagated across all storage locations. eventual consistency, where data might take a brief moment to update everywhere, is often faster for reads and is suitable for many applications. Strong consistency ensures that you always read the very latest data, but it comes with a slight performance trade-off. We'll delve deeper into these nuances later. Your journey begins. This chapter has provided a high-level overview of why NoSQL databases, like Amazon DynamoDB, have become indispensable tools for modern developers. You've learned about the fundamental differences from traditional SQL databases, understood where DynamoDB fits in, and explored the kinds of applications where it truly shines. You've also had your first conceptual glimpse into its core components: tables, items, attributes, and how it handles scaling. In the next chapter, we'll strip away the abstraction and dive deeper into these foundational elements. We'll explore the anatomy of a DynamoDB item, understand the different data types it supports, and lay the groundwork for mastering the most critical aspect of DynamoDB: its primary keys. This knowledge is essential for building robust, scalable, and cost-effective applications with DynamoDB. Let's begin building your expertise one fundamental concept at a time. The DynamoDB fundamentals: tables, items, and attributes. In Chapter 1, we introduced Amazon DynamoDB as a powerful, managed NoSQL database service, ideal for handling modern web-scale applications. We touched upon its core building blocks: tables, items, and attributes. Now, it's time to peel back a layer and delve deeper into these fundamental concepts. Understanding these basics is crucial because they dictate how you structure your data, how you interact with it, and ultimately, how efficiently your application performs. What is a DynamoDB table? Conceptually, a DynamoDB table is similar to a table in a relational database. It serves as a collection of data, logically grouping related information. For example, if you're building an e-commerce application, you might have tables for users, products, and orders. Each table has a unique name within your Oz account and region. For instance, My Web App Users or e-commerce products. However, the similarity largely ends there. Unlike relational tables, which require a rigid, predefined schema for all columns, DynamoDB tables are schemaless. This is a critical distinction and one of DynamoDB's greatest strengths in an agile development environment. The schemaless nature of DynamoDB. In a traditional relational database, before you can add any data, you must define the schema for your table. Create table users. User ID, int primary key. Username varchar, 255. Email varchar, 255, unique. Age int. Every row inserted into this table must conform to this structure. If you later decide to add a phone number or profile picture URL field, you typically need to alter the table schema, which can be an operation with downtime depending on the database and scale. DynamoDB takes a different approach. While you define a primary key when creating a table, we'll cover this in detail next chapter, you don't define the other attributes up front. Each item, which is like a row, can have a different set of attributes. This flexibility means agility in development. You can rapidly iterate on your data models without needing to perform schema migrations. Just start adding new attributes to items as your application evolves. Support for diverse data. Different items within the same table can represent slightly different types of entities or have optional attributes. For example, some user profiles might have a nickname attribute while others don't. This is perfectly acceptable in DynamoDB. Efficient storage. You only store the attributes that are relevant for a particular item, potentially saving storage space compared to relational tables with many null columns. This schema-on-read approach, where the schema is implicitly defined by the data you put in, provides immense flexibility. But it also places more responsibility on your application code to understand the structure of the items it retrieves. Items, the core data unit. An item is the fundamental unit of data in a DynamoDB table. You can think of an item as a collection of attributes, similar to a row in a relational database or a document in a document database. Every item in a table is uniquely identified by its primary key value. Let's imagine a user profile in our users table. An item for a user might look something like this in concept. User ID. User 123. This would be part of the primary key. Username, Alice Smith. Email, alice@example.com. Age, 30. Location, New York. Registration date, 2023 to 1 to 15 T1000Z. Preferences, a complex attribute containing multiple settings. Theme, dark. Notifications, true. Login attempts, 5. Notice a few things here. Each attribute consists of a name, username, email, preferences, and a value. Alice Smith, alice@example.com. Theme, dark. Notifications, true. The user ID attribute is special. It's the primary key that uniquely identifies this item. Some attributes, like preferences, can contain other attributes or even lists of values. Attributes. The data elements. Attributes are the individual data elements that make up an item. They are analogous to columns in a relational table, but with the added flexibility that each item can have different attributes. DynamoDB supports a variety of data types for attributes, categorized as scalar types, number, positive or negative numbers including 0, integers, decimals, scientific notation, e.g. 123, 3.141E5, string, Unicode with UTF-8 encoding, e.g. hello world, username, binary, unencoded byte sequence, useful for storing encrypted data, images, or compressed data. You typically provide this as a base 64 encoded string, e.g. a GVSB G8 GD29 IBGQ equals. Boolean, true or false. Null represents an unknown or undefined attribute. Document types, list, an ordered collection of values. Each value in the list can be of any data type, including other lists or maps. Order is preserved, e.g. red, green, blue, 1, 2, key, value, map, an unordered collection of name-value pairs. Each value in the map can be of any data type, e.g. city, London, country, UK, itemid. P567, quantity, 2, set types, number set, an unordered collection of unique numbers, e.g. 1, 5, 10, string set, an unordered collection of unique strings, e.g. apple, banana, orange. Binary set, an unordered collection of unique binary values, e.g. 1,100,001, 1,100,010. It's important to note that attributes in DynamoDB cannot be empty strings or binary values. If an attribute doesn't have a value, it simply should not exist in the item. This approach helps conserve storage and keeps items concise. Anatomy of an item, an example. Let's put this together with a conceptual example of an order item in an e-commerce orders table. Order ID. Ord hash A1 B2C 3D4, primary key. Partition key and sort key, our focus next chapter. Customer ID, cust hash X9Y8Z7, a string attribute. Order date, 2024 to 3 to 20 T14, 30Z, a string attribute, often used for ISO 8601 timestamps. Total amount, 125.75, a number attribute. Shipping address, a map attribute. Street, 123 Main Cent. City, Anytown. Zip code, 12,345. Items, a list attribute, where each element is a map representing a product in the order. First item in the list, product ID, prod hash P100 string. Quantity, 2 number. Unit price, 25.00, number. Second item in the list, product ID, prod hash P200 string. Quantity, 1 number. Unit price, 75.75, number. Order notes, gift wrapping requested, an optional string attribute, might not exist for all orders. Discount codes used. A string set attribute may be spring 20, FRESHIP. This example demonstrates the flexibility. Each order item can look slightly different. Some might have order notes, some might use discount codes used, others won't. The nested shipping address map and items list illustrate how complex, hierarchical data can be stored naturally within a single item. Small item size implications. While DynamoDB offers flexibility in attribute types and nesting, it's designed for relatively small items, ideally less than 400 KB in size. Larger items will incur higher costs and can become a performance bottleneck. If you have very large documents, you should generally store them in Amazon S3 object storage and link to them from your DynamoDB item. This is a common pattern for storing media files large PDF documents, or extensive logs. Your first interaction with DynamoDB. While we won't be writing actual code yet, understanding the conceptual flow of interaction is helpful. When your application wants to store an item, it will send a put_item request to DynamoDB. This request specifies the table name and the item itself, represented as a collection of name-value pairs for its attributes. DynamoDB then processes this request, storing the item efficiently. Similarly, to retrieve an item, your application sends a getItem request, providing the table name and the item's primary key. The foundation is set. You've now established a solid understanding of DynamoDB's core building blocks: tables as flexible containers, items as individual data records, and attributes as the data elements within those items. You understand the power of its schemaless design and the various data types supported. However, a crucial piece of the puzzle is still missing. How exactly does DynamoDB know where to store an item, and how does it retrieve it efficiently from potentially millions or billions of other items? The answer lies in the primary key. In the next chapter, we will unlock the secrets of primary keys, exploring their critical importance in data modeling and how strategic design of these keys is truly the heart of building performant and scalable DynamoDB applications. Get ready to master the concept that underpins all of DynamoDB's magic: mastering primary keys, the heart of your data model. In the previous chapter, we explored the fundamental building blocks of DynamoDB: tables, items, and attributes. We learned about the schemaless nature of DynamoDB, allowing for incredible flexibility in storing diverse data within a table. However, we deliberately left one critical piece of the puzzle partially explained: the primary key. The primary key is not just a unique identifier for an item. It is arguably the most crucial design decision you will make when building an application with DynamoDB. Why? Because the primary key isn't just about identifying data. It's about how DynamoDB distributes your data, how quickly your data can be accessed, and ultimately, how scalable and cost-effective your application will be. It's the very heart of your DynamoDB data model. When you create a DynamoDB table, specifying a primary key is the only schema definition required. This key uniquely identifies each item in the table, ensuring that no two items can have the same primary key. But its role goes far beyond mere identification. DynamoDB uses the primary key to physically store and retrieve data across its underlying infrastructure, optimizing for rapid lookups. DynamoDB supports two types of primary keys: simple primary key, composed of a single attribute known as the partition key; composite primary key, composed of two attributes, a partition key and a sort key. Let's explore each in detail. The simple primary key, the partition key. A table with a simple primary key means that each item is uniquely identified by a single attribute, the partition key. How it works: when you create a table with a partition key, DynamoDB takes the value of this attribute, processes it through an internal hashing function, and uses the resulting hash value to determine which physical storage partition the item will reside on. Think of these partitions as individual storage bins or shelves in a massive warehouse. When you want to retrieve an item, DynamoDB uses the same hashing function on the partition key value you provide to immediately know exactly which bin to look in. This allows for incredibly fast and direct access to individual items. The analogy of the library section: imagine a vast library where all the books are organized by the first letter of the author's last name. The A section, the B section, and so on. If you want a book by Alice Smith, you go straight to the S section. In this analogy, S is your partition key. You can quickly find where the author's books are located. Critical importance for performance and scalability. The effectiveness of your partition key directly impacts your application's performance and scalability. Uniform distribution. For DynamoDB to achieve consistent, high performance, it's crucial that your data is evenly distributed across its partitions. If all your items, or a disproportionate amount of your access requests, are concentrated on a few specific partition key values, those partitions can become hot, meaning they are overloaded. Avoiding hot partitions. A hot partition is like a single crowded checkout lane at a very busy supermarket while others are empty. All customers' requests are funneled through one lane, causing slowdowns and potential throttling, DynamoDB temporarily rejecting requests to prevent overload. To avoid this, your partition key values should be diverse and requested relatively evenly over time. Choosing a good partition key, high cardinality. Select an attribute that has a large number of unique values. For a user's table, user ID, e.g., a UUID or a unique string identifier, is an excellent choice because each user has a unique ID, ensuring even distribution across partitions. Even access patterns. The values should be accessed fairly uniformly. For example, if you have a votes table for an online poll, using poll ID as a partition key would be bad if one poll receives millions more votes than others, making that poll ID a hot partition. The composite primary key, partition key plus sort key. While a simple primary key is great for direct lookups of individual items, many applications need to perform more complex queries, such as retrieving all items related to a single entity or retrieving items within a certain range. This is where the composite primary key comes in, consisting of a partition key and a sort key. How it works: partition key functions exactly as before. It determines the logical partition where the item is stored. All items with the same partition key value are stored together on the same physical partition. Sort key. Within that partition, items are stored in sorted order based on the sort key value. DynamoDB uses UTF-8 byte ordering for strings and numeric ordering for numbers. The analogy of the library section with book titles. Continuing our library analogy, imagine within the S section your partition key for authors whose last name starts with S. The books are further organized alphabetically by the book's title. If you want all books by Alice Smith, your partition key, you go to the S section, and then you can efficiently browse or retrieve books by title. You could ask for all books by Alice Smith starting with the, or all books by Alice Smith published between 2000 and 2010 if your sort key included date information. Power of the sort key. The sort key unlocks powerful querying capabilities within a single partition. Range queries. You can retrieve a range of items that share the same partition key but have sort key values falling within a specified range, e.g., all orders for a given customer placed in March 2024. Prefix matching. For string sort keys, you can query items whose sort key begins with a specific string, e.g., all comments on an article that start with great point. Combining information. Sort keys often combine multiple pieces of information into a single string, e.g., status hash ordered hash timestamp, to enable multifaceted queries. Examples of composite primary keys. User ID, partition key, ordered sort key for an orders table, access pattern, get all orders for a specific user, query by user ID, access pattern, get all orders for a specific user placed after a certain date, query by user ID with range condition on order ID if order ID includes date info or is sequential. Access pattern, get a specific order for a specific user, query by user ID and exact ordered. Product ID, partition key, reviewed sort key for a product reviews table, access pattern, get all reviews for a particular product. Access pattern, get a specific review for a product. If review ID were structured like rating hash timestamp, e.g., 5 hash 2024 to 3 to 20T10 00Z, you could also query for all 5-star reviews for this product or all reviews for this product written in the last week. Movieid partition key, actor name sort key for a movie cast table. Access pattern, get the entire cast list for a movie. Access pattern, find if a specific actor was in a movie. The access pattern's first mentality, the heart of DynamoDB design. This is paramount. In DynamoDB, you design your data model based on your application's access patterns, how you intend to query and update your data. This is a fundamental shift from relational database design, where you typically normalize your data first and then figure out how to query it. With DynamoDB, you identify all the ways your application needs to retrieve data, and then you design your primary key and later secondary indexes to support those queries efficiently. If your application often needs to retrieve all unread messages for user X, your primary key should probably involve user X and message status. Strategies for choosing optimal partition keys, revisited and expanded. Given the importance of avoiding hot partitions, let's elaborate on strategies for ensuring good partition key choice. High cardinality and even distribution. As discussed, choose an attribute with a wide range of values that are accessed somewhat randomly. Think session ID, user ID, order ID, or IoT sensor ID. Composite partition keys, logical. Sometimes, to achieve uniqueness or better distribution, you might concatenate multiple attributes into a single string for your partition key. For instance, instead of city, which might be hot for large cities, you could use city #neighborhood as your partition key. Adding randomness for extremely high write workloads. If you have a legitimate use case where a short period access pattern will inevitably target a single partition key value, e.g., logging every website click to a website ID, you can introduce artificial randomness. You could append a random number or hash to your partition key, e.g., website ID #random number, creating many logical partitions that map to different physical partitions. You then need to query across these multiple logical keys when reading. This is an advanced technique for extreme scaling. Time series data considerations. For data that accumulates over time, e.g., sensor readings, log entries, using a strict timestamp as a partition key can lead to hot partitions for the current hour/day. Instead, consider device ID as the partition key and timestamp as the sort key. If a device is too chatty, you might need to combine device ID with a date or hour to spread writes for that device over different logical partitions. Common anti-patterns in primary key design. Avoiding these pitfalls is critical. Low cardinality partition keys. Using attributes with a small number of distinct values, e.g., customer segment equals, premium, status equals, active, country equals, USA, will concentrate data on very few partitions, leading to hot partitions and throttling. Sequential partition keys. Using strictly sequential IDs like 1, 2, 3, or timestamps without any randomness as partition keys will direct all new writes to a single or very few partitions and not distribute effectively. DynamoDB's hashing works best with a diverse input. Ignoring access patterns. The biggest mistake is designing your primary key without a clear understanding of how your application needs to fetch data. If your application frequently needs to query by an attribute that isn't part of your primary key, you'll be forced to scan your entire table, which is inefficient and expensive, or rely on secondary indexes, which we'll discuss next. The foundation is laid. You now possess a profound understanding of DynamoDB's primary keys. You know how a simple partition key enables direct, fast lookups and how crucial uniform data distribution is. You've grasped the power of the composite primary key, leveraging the sort key for ordering and efficient range queries within a partition. Most importantly, you now understand the access patterns first principle, which guides all effective DynamoDB data modeling. However, sometimes your primary key, no matter how well designed, won't cover all your application's access patterns. What if you've optimized your primary key for retrieving orders by customer ID and order ID, but you also frequently need to search for orders by product ID? This is where secondary indexes come into play, providing alternative access paths to your data without forcing you to duplicate entire tables. We'll explore these powerful tools in our next chapter. Beyond the basics. Leveraging secondary indexes for flexible queries. In the previous chapter, we established that the primary key is the cornerstone of your DynamoDB data model. Its careful design enables incredibly fast and efficient retrieval of individual items or collections of items that share the same partition key. You learned that thinking access patterns first is paramount, leading you to craft a primary key that satisfies your most frequent and critical data access needs. However, an application often has multiple ways it needs to access data. For example, in an e-commerce application with an orders table, your primary key might be customer ID, partition key, and order ID, sort key. This is perfect for retrieving all orders for a specific customer. But what if you also frequently need to find all orders placed on a specific date, regardless of customer? List all pending orders that require shipping. Identify all orders containing a particular product. Your primary key won't directly support these queries efficiently. Trying to find orders by order date or product ID would force you to scan the entire table, which is an inefficient and expensive operation, similar to reading every single book in a library just to find one by its publication date, when the library is only organized by author. This is where secondary indexes come into play. Secondary indexes provide alternative access paths to your data, allowing you to query your table using attributes other than the primary key. They essentially create a separate, sorted view of a subset of your table's data, built and maintained automatically by DynamoDB. DynamoDB supports two types of secondary indexes: local secondary indexes, LSIs, global secondary indexes, GSIs. While both serve the purpose of enabling flexible queries, they have distinct characteristics, use cases, and implications for consistency and performance. Local secondary indexes, LSIs. A local secondary index is conceptually an alternative sort key for your main table. Crucially, an LSI shares the same partition key as the base table, but it has a different sort key. Key characteristics of LSIs. Same partition key. The partition key of an LSI must be identical to the partition key of its base table. This means all items with the same LSI partition key value are stored within the same logical partition as the base table. Different sort key. The sort key of an LSI can be any non-key attribute from the base table. Strongly consistent reads. Reads from an LSI can be strongly consistent. This means that when you read data from an LSI, it will reflect all successful write operations that occurred before the read. This is a significant advantage where immediate data accuracy is paramount. Limited size. The total size of all items with the same partition key across the base table and all its LSIs cannot exceed 10 gigabytes. This is because all data for a given partition key is physically grouped together. Defined table creation. You must define LSIs when you create the table. You cannot add, modify, or delete an LSI after the table has been created. Costs. LSIs consume read and write capacity units, RCUs, WCUs, separately from the base table, but they don't have their own provisioned throughput capacity. Instead, they share the read and write capacity of the base table. When to use an LSI? Use an LSI when you need to query data using an alternative sort key. You frequently query operations that target a single partition key but need different sorting or filtering based on other attributes. You require strongly consistent reads for the query. The 10 GB per partition key limit is not an issue for your data. Conceptual example: user purchases. Let's say you have a purchases table where the primary key is user ID, partition key, and purchased sort key. This allows you to easily get all purchases for a user. Now, imagine you want to retrieve all purchases for a user, sorted by the purchase date, which is an attribute in your item, not the sort key. You could create an LSI. LSI partition key. User ID, same as base table. LSI sort key. Purchase date, attribute from your base table. Now, within the context of a single user, you can efficiently query their purchases sorted by date. Global secondary indexes, GSIs. Global secondary indexes are far more flexible and powerful than LSIs because they have their own partition key and sort key that can be different from the base table's primary key. A GSI is essentially a completely separate table that DynamoDB automatically maintains and keeps synchronized with your main table. Key characteristics of GSIs: independent keys. The partition key and sort key of a GSI can be any attribute from the base table, including attributes that are not part of the base table's primary key. This is the biggest difference from LSIs. Eventually consistent reads. Reads from a GSI are eventually consistent. This means that data changes from the base table might take a short period, typically milliseconds, to propagate to the GSI. A read might return stale data if a write operation just occurred. For many applications, this slight delay is acceptable. If you absolutely need the latest data, you must read directly from the base table using its primary key. Not unique. Unlike the base table's primary key, the combination of partition and sort key in a GSI does not have to be unique. If multiple items in the base table have the same GSI key values, All of them will appear in the GSI when queried. Independent throughput. GSIs have their own dedicated read and write capacity units, RCUs, WCUs, that you provision or use on demand, separate from the base table. Writes to the base table consume WCUs on the base table and the affected GSIs. No size limit. There is no 10 GB per partition key limit for GSIs, as they operate as independent tables. Defined at any time, you can add, modify, or delete GSIs at any time on an existing table. When to use a GSI when you need to query data using attributes that are different from your base table's partition key. Your query patterns require retrieving data based on attributes that are not part of the base table's primary key. You need to support queries that span across multiple partition keys in the base table, e.g., give me all products from category X, where category X is not your base table's partition key. Eventually, consistent reads are acceptable. You need to project specific attributes to optimize cost and performance for the index. Conceptual example, product catalog. Consider a products table with a primary key of product ID, partition key. This is great for looking up products by their unique ID. Now, imagine you frequently need to find all products within a certain category. Find all products made by a specific manufacturer. Here you would create GSIs, GSI1 category index, GSI partition key, category, GSI sort key, product name or product ID for uniqueness within category if desired. This GSI allows you to efficiently query for all products in a given category, potentially sorted by product name. GSI2 manufacturer index, GSI partition key, manufacturer, GSI sort key, model number or product name. This GSI allows you to efficiently find all products from a specific manufacturer. Projections, what data goes into the index? When you create a secondary index, you specify which attributes from the base table are projected, copied into the index. This is crucial for managing index size, performance, and cost. There are 3 projection types. KEYSONLY, only the primary key attributes of the base table and the index's key attributes, partition key and sort key, are projected into the index. This makes the index very small and cost-effective, but if you need other attributes, you'll have to perform an additional read operation against the base table, a fetch. Include. In addition to the key attributes, you can specify a list of additional non-key attributes to be projected into the index. This is useful if your query pattern always needs a few specific attributes, e.g., product name, price, that aren't part of the index's key. This avoids the extra fetch step. All attributes from the base table item are projected into the index. This makes your queries faster as you never need to fetch from the base table, but it also makes the index larger, increasing storage costs and write throughput costs, as all attribute updates on the base table also need to be written to the index. Choosing a projection type, KEYSONLY, use when you primarily need to get a list of keys and then fetch full item details from the base table as needed. Good for saving costs. Include a balanced approach. Project only the attributes essential for your specific query pattern on that index. All. Use when you frequently query the index and need access to almost all item attributes, and the performance benefit outweighs the increased cost. Use with caution, especially for large items. Secondary indexes in action, the power of multiple access paths. Let's revisit the orders table example, now with indexes. Base table, orders. Primary key, customer ID partition key, order ID sort key. Attributes, customer ID, order date, delivery status, product ID, quantity, total amount. Access pattern 1, get all orders for a specific customer. Solution, query the base table using customer ID. Access pattern 2, find all pending orders where delivery status is pending. Solution, create a GSI partition key. Delivery status, GSI sort key, order date to get pending orders by date. Projection, include customer ID, order ID, total amount. This GSI allows you to query delivery status, pending, efficiently. Access pattern 3, get all orders placed on a specific date. Solution, create another GSI partition key, order date. GSI sort key, order ID. Projection, include customer ID, delivery status. This GSI allows you to query for orders by exact date. Notice how each GSI effectively provides a new entry point into your data, tailored for a specific type of query. Considerations and trade-offs. While secondary indexes offer immense flexibility, they come with trade-offs. Increased write costs. Every time an item in your base table is created, updated, or deleted, DynamoDB must also update all associated secondary indexes. This consumes additional write capacity units on both the base table and the indexes themselves. For GSIs, more indexes mean higher write costs. Increased storage costs. Indexes store a copy of some or all of your base table data. Larger indexes mean higher storage costs. Consistency, GSI limitation. Remember that GSIs are eventually consistent. If your application demands absolute, immediate consistency for a query, you must perform that query directly on the base table using its primary key. Query limits. Similar to the base table, queries on indexes usually return a maximum of 1 MB of data per request, requiring pagination for larger result sets. Conclusion: your expanded toolkit for data access. By mastering secondary indexes, you've significantly expanded your ability to design performant and flexible DynamoDB data models. You now have the tools to serve diverse access patterns that go beyond simple primary key lookups. You understand that LSIs are for alternative sort orders within the same partition, offering strong consistency, but with limitations. You also grasp that GSIs are far more powerful, providing completely different querying capabilities across your data, albeit with eventual consistency. Knowing when to use which type and how to effectively project attributes is key to optimizing both performance and cost. With your understanding of tables, items, attributes, primary keys, and now secondary indexes, you have the foundational knowledge to truly sculpt your data for efficiency. The next step is to translate this knowledge into practical application interaction. In the upcoming chapter, we'll shift our focus to how developers actually build applications using DynamoDB, covering the fundamental create, read, update, and delete (CRUD) operations, and how to interact with the database using AWS SDKs. Building your application, CRUD operations, and SDKs. We've now laid a strong theoretical foundation, understanding DynamoDB's structure, tables, items, attributes, the crucial role of primary keys, and the flexibility offered by secondary indexes. These concepts are powerful in designing your database. But how do you actually use DynamoDB from your application? How does your code interact with the database to store, retrieve, update, and delete information? This chapter bridges that gap. We'll explore the fundamental operations known as CRUD, create, read, update, delete, and discuss how developers typically interact with DynamoDB using the AWS Software Development Kits, or SDKs, and the AWS Command Line Interface, CLI. While we'll focus on the conceptual flow relevant for both print and audio, understand that these operations map directly to specific functions or methods in your chosen programming language's Oz SDK. The AWS SDKs and CLI, your gateway to DynamoDB. To interact with any AWS service, including DynamoDB, developers use provided interfaces. AWS Software Development Kits, SDKs. These are libraries available for popular programming languages like Python, Node.js, Java, Net, Go, PHP, Ruby, etc. They abstract away the low-level details of making HTTP requests to AWS APIs, handling authentication, retry logic, and error parsing. When you hear about putitem or getitem, these are typically methods within the SDKs. AWS Command Line Interface, CLI, a powerful tool for interacting with Oz services from your terminal. It's excellent for scripting, automation, and quick ad hoc operations. Many of the SDK operations have direct CLI equivalents. DynamoDB Console. The web-based console provides a graphical interface for managing your DynamoDB tables, viewing items, and performing basic operations. It's useful for quick checks and learning, but not for programmatic interaction. For programmatic application development, the Oz SDKs are your primary interface. They provide the most streamlined and robust way to communicate with DynamoDB. Basic CRUD operations. Let's break down the core operations for manipulating data within a DynamoDB table. 1. Create or replace. Put item. The put item operation is used to create a new item or to completely replace an existing item. Conceptual flow. Your application constructs an item, providing all its attributes, including the complete primary key value, partition key, and, if applicable, sort key. It sends this item to DynamoDB using the put item operation, specifying the target table. If an item with the same primary key already exists, put item will overwrite the existing item, replacing it entirely with the new item provided. This behavior makes put item useful for both creation and full replacement. If no item with that primary key exists, a new item is created. Important use case. Conditional writes. Often, you don't want to blindly overwrite an item. You might want to create an item only if it doesn't already exist, or update it only if a specific attribute has a certain value. Put item supports condition expressions for this. Conceptual example. Add a new user to the users table, but only if a user with that user ID doesn't already exist. If it does, prevent the write. This is crucial for ensuring data integrity and preventing accidental overwrites, especially in concurrent environments where multiple users or processes might try to write to the same item simultaneously. 2. Read, get item. The get item operation is the simplest and most efficient way to retrieve a single item from a DynamoDB table using its primary key. Conceptual flow. Your application specifies the target table and the full primary key of the item it wants to retrieve. It sends this request to DynamoDB using getItem. DynamoDB retrieves the item, if it exists, and returns its attributes to your application. Key characteristics of getItem. Most efficient. getItem is highly optimized because DynamoDB knows exactly which partition to go to and where to find the item. Direct access. It provides direct access based on the full primary key. You cannot use getItem to search for items based on other attributes. For that, you need query or scan. Consistency control. By default, getItem performs an eventually consistent read. This is generally faster. However, you can explicitly request a strongly consistent read if your application requires the absolute latest data. Conceptual example. Retrieve the profile for user ID, user 123, from the users table. 3. Update item. The update item operation allows you to modify existing attributes of an item without replacing the entire item. This is often preferred over put item for updates, especially if items can be large or have many attributes, as it's more efficient to modify only the necessary parts. Conceptual flow. Your application specifies the target table and the full primary key of the item to update. It defines an update expression that specifies how to modify attributes, set, add new attributes, or change existing ones. Remove. Delete attributes, ADD, increment decrement numbers, or add elements to a set. Delete, remove specific elements from a set. It sends this to DynamoDB using update item. Important use case. Atomic counters. A common pattern is to increment or decrement a number. Update item supports atomic counters, ensuring that even if multiple operations try to update the same counter concurrently, the final value is correct. This is vital for things like view counts, upvote totals, or remaining inventory. Conceptual example. For the item with user ID, user 123 in the users table, change the email attribute to new email at example.com. Increment the login attempts attribute by 1. Remove the temporary flag attribute. Like put item, update item also supports condition expressions to ensure that updates only occur if certain conditions are met, enhancing data integrity. 4. Delete item. The delete item operation is used to remove an item from a table. Conceptual flow. Your application specifies the target table and the full primary key of the item to delete. It sends this request to DynamoDB using delete item. DynamoDB removes the item. If the item doesn't exist, the operation still succeeds, it's idempotent. Conceptual example. Delete the item for user ID, user 456, from the users table. Delete item also supports condition expressions if you only want to delete an item under specific circumstances, e.g., Delete this order only if its status is canceled. Beyond single-item operations, query and scan. While getItem retrieves a single item, applications often need to retrieve groups of items. This is where query and scan come in. Query. The query operation is used to retrieve all items that share the same partition key value. You can then optionally filter and sort these items based on the sort key of the primary key or a secondary index. Conceptual flow. Your application specifies the target table or a secondary index and a specific value for its partition key. Optionally, it provides conditions for the sort key, e.g., begins with, between, greater than. Sends the request to DynamoDB using query. DynamoDB efficiently retrieves only the items within that specific partition that match the criteria. Key characteristics of query: targeted and efficient. Query is highly efficient because it targets a single partition or a single partition within an index. It's the primary way to retrieve multiple related items. Uses primary key or index keys. You must always provide an exact match for the partition key. You can't query solely on a sort key. Result ordering. Results are returned sorted by the sort key, ascending by default, but you can request descending. Pagination. If a query's result set exceeds 1 MB, DynamoDB returns the first 1 MB of data along with a last evaluated key. Your application must then make subsequent query calls, with the last evaluated key as the exclusive start key, to retrieve the next page of results until all items are fetched. Conceptual example. From the orders table, PK, customer ID, SK, order ID, query for all orders belonging to customer ID, CUSD 789. Query for all orders belonging to customer ID, CUSD 789, that were placed after 2024 to 3 to 1, using a range condition on order ID if it incorporates time. Scan. The scan operation reads every item in the specified table or secondary index. It then optionally filters the results to return only the items that match a specific condition. Conceptual flow. Your application specifies the target table or a secondary index. Optionally, it provides a filter expression to narrow down the results after all items have been read. Sends the request to DynamoDB using scan. DynamoDB reads literally every item in the table index, applies the filter, and returns the matching results. Key characteristics of scan: inefficient for large tables. Scan is generally inefficient and expensive for large tables because it reads all data, consumes a lot of read capacity, and can be slow. It's akin to flipping through every single page in every single book in the entire library to find a specific word. Best for small tables or infrequent operations. Use scan only for very small tables or for infrequent administrative tasks, such as creating a backup, exporting data, or performing a periodic analysis that doesn't need to be real-time. Pagination. Like query, scan results are paginated at 1 MB bursts. Conceptual example. From the products table, scan the entire table and apply a filter to find all products where price is less than 10.00. Note, this is an example of how it works, not a recommendation for large tables. Batch operations, efficiency for many items. DynamoDB also offers batch operations for efficiency. Batch getItem retrieves up to 100 items from one or more tables in a single request, using their primary keys. This is more efficient than making 100 individual getItem requests. Batch writeItem puts or deletes up to 25 items across one or more tables in a single request. This is efficient for bulk writes or deletes, but there's no way to perform conditional writes within a batch. Error handling and idempotency. When interacting with any distributed system like DynamoDB, it's crucial to consider error handling and idempotency. Error handling. Your application should be prepared to handle various exceptions, such as provision throughput exceeded exception, meaning you've tried to consume more capacity than available, or conditional check failed exception, when a condition expression fails. Oz SDKs often include automatic retry mechanisms, but your application code needs to manage more complex scenarios. Idempotency. An idempotent operation is one that can be safely repeated multiple times without changing the result beyond the initial application. For example, delete item is naturally idempotent. Deleting an item that doesn't exist has no side effects. Put item with a conditional expression, e.g., put if not exists, is also idempotent. For update item or put item without conditions, you might need to implement idempotency tokens or version numbers in your application logic to prevent duplicate processing if a request retries. Next steps. Moving beyond the basics, you now understand the fundamental operations for interacting with DynamoDB. You know how to create, retrieve, update, and delete individual items efficiently using put item, get item, update item, and delete item. You also see how to retrieve sets of items using query, efficient and targeted, and scan, less efficient, uses for specific cases. This direct manipulation of items is powerful, but effectively using DynamoDB for complex applications requires more than just knowing the API calls. It requires sophisticated data modeling strategies that anticipate how your application will access data. In the next chapter, we'll dive deeper into advanced data modeling patterns that leverage all the concepts we've covered so far, showing you how to build highly scalable and performant applications by designing your data for access. Advanced data modeling patterns for scalable applications. Up to this point, we've focused on the foundational elements of DynamoDB: tables, items, attributes, and how primary and secondary keys enable efficient data access. We've also touched upon the fundamental CRUD operations that allow your application to interact with your data. Now, we arrive at one of the most critical and distinct aspects of working with DynamoDB: data modeling. In the relational world, the mantra is often normalize, normalize, normalize. You strive to eliminate data redundancy, break information into discrete tables, and then join them together to reconstruct complex views. This approach optimizes for storage efficiency and data integrity, relying on the database's ability to perform complex joins. In DynamoDB, the philosophy is almost the inverse. Because DynamoDB is designed for lightning-fast reads and writes at massive scale, and it doesn't support joins, your data modeling approach must prioritize access patterns above all else. This often means denormalization, duplicating data, or combining related entities into a single table. To ensure that a single query or a minimal number of queries can retrieve all the data an application needs for a specific feature. This chapter delves into advanced data modeling patterns that are common and highly effective for building scalable applications with DynamoDB. These patterns demonstrate how to use your primary keys, sort keys, and secondary indexes creatively to meet diverse access requirements. 1. Single table design, the DynamoDB superpower. Perhaps the most significant paradigm shift when moving to DynamoDB is the adoption of single table design. Instead of creating a separate table for every entity type, e.g., users table, orders table, products table, a single table design often combines multiple entity types into one large table. Why single table design? Reduced cost. Fewer tables mean fewer provisioned RCUs, WCUs overhead if using provisioned capacity. Improved performance. Data for a single access pattern can often be fetched with one query operation, eliminating the need for application-side joins and reducing network round trips. Operational simplicity. Fewer resources to manage. Enhanced scalability. By co-locating related data on the same partition, you maximize the efficiency of DynamoDB's horizontal scaling. How it works: conceptual example. Imagine a customer service application. Instead of separate tables for customers, orders, products, and support tickets, you could use one table, say customer service data. The magic lies in how you design your partition key, PK, and sort key, SK, to represent different entity types and their relationships. You'll often use prefixes in your key values to differentiate entity types. Example: customer and order data. Your single table might have items structured like this: customer item, PK, customer hash customer ID, e.g., customer hash 123, SK profile, attributes, customer ID, name, email address, etc. Order item, PK, customer hash customer ID, e.g., customer hash 123, SK, order hash order ID, e.g., order hash 456. Attributes: orderid, order date, total, status, items, nested list of product IDs and quantities, etc. Access patterns enabled. Get a customer's profile. Query where PK equals customer hash customer ID and SK equals profile. Get all orders for a customer. Query where PK equals customer hash customer ID and SK begins with order. Get a specific order for a customer. Query where PK equals customer hash customer ID and SK equals order hash order ID. Notice how the PK remains customer hash customer ID for both the customer profile and their orders, ensuring that both related types of data are collocated within the same partition. This makes retrieving a customer's profile and all their orders a single, efficient query operation. You can extend this further. Add product SKU details. PK, product hash product ID, SK. Metadata, customer reviews of a product. PK, product hash product ID, SK, review hash customer ID. Support tickets for a customer. PK, customer hash customer ID, SK. Ticket hash ticket ID. Single table design often involves clever use of global secondary indexes, GSIs, to support access patterns that don't align with the main table's primary key. For instance, if you need to find all customer support tickets based on ticket status, e.g., open, across all customers, you design a GSI where the GSI PK is ticket status and the GSI SK is ticket hash ticket ID. 2. Modeling one-to-many relationships. One-to-many relationships are very common, e.g., one customer has many orders. Option 1, collocation using sort key. As seen in single table design, the most efficient way to model one-n relationships is to put the many side items on the same partition as the one side, using the partition key to link them. E.g., customer hash user ID PK, order hash order ID SK for orders. Customer hash user ID PK, address hash address ID SK for multiple addresses. Option 2, nesting for limited many items. If the many side is always limited in number and doesn't require individual querying, you can nest them as a list or map within the one item. E.g., a user item having a phone numbers attribute, which is a list of strings 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. This is good for small, bounded lists. However, if you need to query by a specific phone number, this approach is bad. 3. Modeling many-to-many relationships. Many-to-many relationships, e.g., students can enroll in many courses, and courses can have many students, are more complex. There are several patterns. Option 1, adjacency list pattern, most versatile. This pattern is ideal for representing graph-like structures where entities can have multiple relationships with each other. It uses a single table with a generic primary key composed of PK and SK. Conceptual example, social network connections. Table social graph. PK, user hash user ID 1. SK, following hash user ID 2. User 1 follows user 2. SK, followed by hash user ID 3. User 3 follows user 1. SK, isfrn with hash user ID 4. SK, group member of hash group ID. This pattern lets you query all relationships for a given user. For example, PK equals user hash user ID 1 and SK begins with following hash, gets all users that user ID 1 follows. To find who is following user ID 1, you could then create a GSI with the GSI PK as the SK of the main table, and the GSI SK as the PK of the main table. So, GSI PK equals following hash user ID 1, GSI SK equals user hash user ID who follows to find followers. Option 2. Composite key in an intermediary table, simpler, less flexible for complex queries. Like relational databases use a junction table, you can create a table specifically for the many-to-many relationship. Conceptual example, students and courses. Table enrollments, PK, student hash student ID, SK, course hash course ID. This allows querying a student's enrolled courses. To query all students in a course, you'd need a GSI. GSI PK, course hash course ID, GSI SK, student hash student ID. Option 3, denormalization for bounded relationships. If the many side is small and bounded, you can denormalize by embedding lists of IDs. Student item, PK equals student hash ID, SK equals profile enrolled courses. Course hash ABC, course hash def. Course item, PK equals course hash ID, SK equals metadata enrolled students. Student hash 123, student hash 456. Caveat, this is efficient for reads, but complex for updates and querying by the embedded list contents requires scan operations, making it unsuitable for large numbers of relationships or frequent lookups on the embedded side. 4. Hierarchical data and trees. Representing hierarchies, like document paths, nested comments, organizational structures, can also be done within a single table. Conceptual example: file system paths, table file system, PK path hash parent path, hash of parent path, SK file hash file name or dir hash directory name. A GSI could be used for the exact opposite, to find an item by its full path if the main table's PK-SK combination is not suitable for that. Conceptual example: nested comments threads, PK thread hash thread ID, SK comment hash timestamp hash comment ID. Here, comment hash timestamp sorts the comments, and you can retrieve all comments for a thread easily. Comment ID is added for uniqueness if multiple comments can occur at the same timestamp. 5. Time series data. Storing large volumes of time series data, e.g., IoT sensor readings, log data, requires careful partition key design to prevent hot partitions and enable efficient querying by time. Primary pattern, PK. Device hash device ID hash date, e.g., device hash ABC hash 2024 to 3 to 20. SK. Timestamp hash full timestamp, e.g., timestamp hash 2024 to 3 to 20 T10 3015Z. This ensures all readings for a day from a device are on the same partition, easily queryable by device ID and date, and sortable by timestamp. If a single device produces too much data for a single day, consider making the PK even more granular, e.g., device ID hash date hash hour, or even introducing artificial randomness, discussed in Chapter 3, by adding a random suffix to the PK like device ID hash date hash RND shard. For reads, you would then query multiple shards. Strategic denormalization. Denormalization is a common tactic in DynamoDB modeling. This means intentionally duplicating data across items or tables to optimize for read performance, especially when there are no joins available. Conceptual example. In our e-commerce orders table example, each order item may contain a customer ID and customer name. If the customer's name changes, you would need to update all past order items or accept that past orders reflect the old name. In a relational database, you just update the customer's table, and all linked orders would reflect the change. In DynamoDB, you must weigh freshness. Is it critical that all historical data reflects the latest customer name? If so, you'll need a mechanism, like DynamoDB streams and Lambda functions, which we'll cover later, to propagate updates. Read performance. Is it critical to retrieve the customer name along with the order details in a single read without making an additional lookup to the customer table? If so, denormalization is beneficial. The decision to denormalize is a balance between read performance, write cost, and data consistency requirements. The access patterns first mindset. A recap. This chapter brings home the central philosophy of DynamoDB data modeling. Focus on your access patterns first. List all known access patterns. Before you design anything, write down every single way your application will need to query or update data. Be specific. Get a user by ID, get all products in a category, get all pending support tickets. Design primary keys for main access patterns. Choose your PK and SK for the table to satisfy the most frequent and critical queries. Use GSIs for alternative access patterns. If an access pattern can't be efficiently served by the main table's primary key, devise a GSI whose keys match that pattern. Denormalize strategically. Duplicate data where necessary to avoid multiple round trips or complex application-side joins. Iterate and refine. Data modeling is not a one-time thing. As your application evolves, your access patterns may change, requiring adjustments to your schema. By embracing these patterns and the access patterns first mindset, you can build incredibly performant, scalable, and cost-effective applications with DynamoDB. You're no longer constrained by the rigid structure of traditional databases, but empowered by DynamoDB's flexibility and horizontal scalability. We've covered the core concepts and advanced modeling techniques. The next step in your DynamoDB journey is to understand how to ensure data integrity and global reach. In the upcoming chapter, we'll explore DynamoDB transactions for managing atomic operations and global tables for multi-region replication, taking your application's reliability and resilience to the next level, ensuring consistency and isolation, transactions and global tables. So far, we've focused on building scalable data models and interacting with individual items or groups of items within a DynamoDB table. We've learned how highly performant and flexible single-item operations are. However, production applications often require more than just individual item manipulation. They need ways to ensure data integrity across multiple operations and to provide users with a consistently fast experience, regardless of their global location. This chapter addresses these critical aspects by introducing two powerful DynamoDB features: transactions for ensuring atomicity across multiple operations, and global tables for achieving multi-region data replication and high availability. DynamoDB transactions, achieving ACID properties. In traditional relational databases, you are familiar with the concept of transactions, which are sets of operations treated as a single, indivisible unit. They adhere to the ACID properties, atomicity. All operations in the transaction succeed or none of them do. It's an all-or-nothing proposition. Consistency. A transaction brings the database from one valid state to another. Isolation. Concurrent transactions execute in such a way that the result is as if they had executed sequentially. Durability. Once a transaction is committed, its changes are permanent and will survive system failures. While DynamoDB is a NoSQL database that generally prioritizes availability and partition tolerance over strict consistency, following the base principles for eventual consistency by default, it now offers transactional operations to meet the ACID requirements for specific use cases. This is especially useful for business-critical applications where data integrity across multiple data operations is paramount. DynamoDB provides two main transactional APIs: transact_write_items, for writing, adding, updating, deleting multiple items as a single, all-or-nothing operation; transact_get_items, for reading multiple items as a single, consistent snapshot. How transact_write_items works. Imagine a scenario where a user purchases an item online. This single purchase logically involves multiple database updates: decrement the item's inventory account, create a new order item, update the user's purchase history. If any of these operations fail, e.g., inventory is suddenly insufficient or a network error occurs during order creation, you don't want a partial update. Transact_write_items ensures that either all these changes are successfully applied, or none of them are. If one operation fails, the entire transaction is rolled back, leaving the database exactly as it was before the transaction began. Key characteristics of transact_write_items. Atomicity guarantees that all operations within the transaction succeed or fail together. Maximum operations supports up to 10 unique operations within a single transaction. These operations can be across different tables, as long as they are within the same OZ account and region. Conditional checks. Each operation within a transaction can include its own conditional check, e.g., only decrement inventory if inventory count is greater than 0. If any conditional check fails, the entire transaction fails. Cost. Transactional writes consume 2x the standard write capacity units for each operation, because DynamoDB needs to perform additional internal operations to ensure atomicity. Conceptual example: fund transfer. A classic use case for transactions is a fund transfer between two bank accounts. Decrement amount from account A balance. Increment amount to account B balance. If account A doesn't have sufficient funds, or if any error occurs during the transfer, you want to ensure no money is lost or created in thin air. Transact_write_items ensures this all-or-nothing outcome. How transact_get_items works. Transact_get_items allows you to read up to 10 items from one or more tables as a single, consistent snapshot. This means that all the items returned by the transaction reflect the state of the database at the exact same point in time. Key characteristics of transact get items. Snapshot isolation. All reads are performed as if they executed simultaneously, guaranteeing that you don't read partial or in-progress updates from other transactions. Consistency. Always performs strongly consistent reads. Cost. Transactional reads consume 2x the standard read capacity units for each operation. Conceptual example. Complex business view. Imagine displaying a user's dashboard that requires data from their profile item, their active orders, and their notification preferences. To ensure the dashboard always shows a coherent view and not a mix of old and new data, transact get items can retrieve all 3 items as a single, consistent unit. When to use DynamoDB transactions. When your application requires ACID properties across multiple item operations. When a business process must not result in a partially updated state. When you need to perform multiple conditional updates together. When you need a consistent view of multiple items at a single point in time. When not to use transactions or use with caution. For single item operations, where standard put item, update item, delete item with conditions are sufficient and more cost-effective. For very high volume, performance-critical paths where the 2x RCU/WCU cost or the slightly increased latency of transactions might be prohibitive. When your operations exceed the 10-item limit. Global tables, multi-region high availability and low latency. As applications expand globally, providing a fast and reliable experience to users in different geographic regions becomes critical. While DynamoDB's single-region deployment offers high availability and durability within that region, it can't magically overcome the speed of light for users accessing from across continents. This is where global tables come in. A DynamoDB global table is a fully managed, multi-region, multi-active database. It enables you to deploy a highly available and highly performant application that serves users located anywhere in the world. A global table consists of multiple replica tables, one in each chosen AWS region. When your application writes data to any one of these replica tables, DynamoDB automatically and asynchronously propagates that change to all other replica tables in other regions. Key characteristics of global tables. Multi-active, active-active. All replica tables are fully readable and writable. An application can write to the replica closest to its users, and the changes will be replicated globally. This means users globally can benefit from low-latency reads and writes to their nearest region. Automatic asynchronous replication. Once you enable global tables, DynamoDB handles all the complex background work of replicating data changes between regions. You don't need to write any custom replication logic. Disaster recovery. If an entire AWS region experiences an outage, your application can automatically fail over to a healthy replica table in another region, significantly reducing recovery time objectives, RTO, and recovery point objectives, RPO. Eventual consistency for replication. While individual writes to a replica are consistent within that region, the replication between regions is eventually consistent. This means there might be a brief propagation delay before a change made in one region appears in a replica in another region. Conflict resolution. In an active-active setup, it's possible for the same item to be updated almost simultaneously in different regions. DynamoDB global tables use a last writer wins conflict resolution strategy. The update with the most recent timestamp is the one that prevails. This is simple and effective for many use cases, but it's important to understand the implications for your application design when concurrent writes to the same item from different regions are a concern. Simplified operations. DynamoDB manages the entire replication pipeline, including ensuring data consistency and handling network issues between regions. Conceptual example. Global User Profile Service. Imagine a global social media platform where users can update their profile information, e.g., bio, profile picture, from anywhere in the world. A user in Europe updates their profile. Their application writes to the DynamoDB replica in EU West 1, Ireland. DynamoDB automatically replicates this change to its replicas in US East 1, Virginia, and App Southeast 2, Sydney. A user in the US views that profile. Their application reads from the US East 1 replica, experiencing low latency. When to use global tables, global applications. When your user base spans multiple continents and requires consistently low latency for both reads and writes. Disaster recovery, low RTO/RPO. When your application has strict requirements for business continuity and needs to recover quickly from a regional outage with minimal data loss. High availability. When your architecture demands that your database remains operational even if an entire AWS region becomes unavailable. When not to use global tables or use with caution, regional-only applications. If your users are all concentrated in a single geographical region, global tables add unnecessary cost and complexity. Strict serializability. Asterisk, if your application absolutely requires that writes to the same item from different regions never conflict and are always processed in a perfectly sequential, globally synchronized order, the last writer wins strategy might not be sufficient. In such niche cases, a single region deployment might be necessary, or custom application-level conflict resolution would be required. Increased cost. You pay for the read and write capacity in each asterisk replica region, plus data transfer costs for replication between regions. Conclusion: robustness for critical applications. DynamoDB transactions and global tables significantly enhance the robustness and reliability of your DynamoDB-backed applications. Transactions empower you to maintain data integrity for critical multi-item operations, providing the ACID guarantees necessary for many business processes. Global tables, on the other hand, unlock truly global, highly available, and low-latency access to your data, making your applications resilient to regional failures and providing an optimal experience for users worldwide. With these tools, you can build applications that not only scale immensely, but also stand up to the most stringent requirements for data consistency and operational continuity. However, keeping a high-performance database running optimally also requires constant vigilance. Your users expect data to react in real time, and your application needs to respond swiftly to changes. In the next chapter, we will explore DynamoDB streams and triggers, discussing how you can build event-driven architectures that react instantly to changes within your DynamoDB tables, enabling real-time processing, analytics, and integrations. Reacting to change, DynamoDB streams and triggers. In the journey so far, we've learned how to model our data, perform CRUD operations, and even ensure transactional consistency and global availability. These are all crucial for managing the current state of our data. But what if your application needs to react to changes in data as they happen? What if a new user registration needs to trigger a welcome email, or an order update needs to push a notification to a fulfillment system, or new sensor data needs to be analyzed in real time? This is where DynamoDB streams and DynamoDB triggers come into play. They enable you to build powerfully reactive, event-driven architectures, extending the functionality of your application beyond simple data storage and retrieval. DynamoDB streams, the event log. At its core, a DynamoDB stream is a time-ordered sequence of item-level modifications in a DynamoDB table. Think of it as a continuous, detailed log of every single change that occurs in your table, recorded in the exact order in which they happened. Every time your application, or any process, creates, updates, or deletes an item in a DynamoDB table, an event is captured and written to the table's stream. What kind of information does a stream capture? When you enable a stream on a table, you specify the stream view type, which determines the information captured in the event record. KEYSONLY. Only the primary key attributes of the modified item are written to the stream. This is useful if you only need to know which item changed, but not what changed. NEWMG. The entire item as it appeared after it was modified is written to the stream. This is like getting a snapshot of the item's new state. OLDIMAG. The entire item as it appeared before it was modified is written to the stream. This is useful for understanding what values were changed from. NEWNDULDMAGS. Both the new image and the old image of the item are written to the stream. This provides the most comprehensive information, allowing you to compare the before and after states and determine exactly what attributes changed and how. This is often the most useful view type. Each record in a DynamoDB stream also includes metadata such as the event name, e.g., insert, modify, remove, the event ID, the DynamoDB table name, the approximate creation time of the event, how long are stream records available. DynamoDB streams store records for 24 hours. If your application or process doesn't read the records within this timeframe, they expire and become unavailable. This means stream consumers must process events relatively quickly. DynamoDB triggers, reacting with AWS Lambda. While DynamoDB streams capture change events, they don't do anything with those events on their own. This is where DynamoDB triggers come in, which is essentially an AWS Lambda function you configure to automatically invoke whenever new records appear in a DynamoDB stream. Conceptual flow. An item is modified in your DynamoDB table. E.g., a new user signs up and order status changes. DynamoDB captures the event and writes it to the table's stream. DynamoDB sends a batch of new stream records to your configured AWS Lambda function. Your Lambda function executes. It processes these records, accessing the new image, old image, or just the keys, depending on how you configured your stream view type. Your Lambda function performs an action based on the event. This action can be virtually anything: sending a notification, updating another database, invoking another AWS service, performing complex business logic. This pattern is a powerful example of an event-driven architecture. Your application now effectively listens for changes in your data and can react to them in real time without needing to constantly poll the database for updates. Common use cases for DynamoDB streams and triggers. The combination of streams and Lambda unlocks a wide range of real-time capabilities for your applications. Real-time analytics and dashboards. Scenario. You store user activity data in a DynamoDB table. You want to see real-time trends on active users, popular features, or conversions. Solution. Enable a stream on your activity table. A Lambda function processes each new activity event, aggregates key metrics, and updates a separate dashboard table or pushes data to an analytics service for visualization. Search indexing. Scenario. Your application has a user-facing search feature that needs to be constantly up to date with the latest product or document information stored in DynamoDB. Solution. Use a stream to capture item updates. A Lambda function processes these updates and pushes the relevant item data to a search service like Amazon Open Search Service, formerly Elasticsearch Service, or Algolia, ensuring your search indexes are always fresh. This effectively decouples your transactional database from your search engine. Cross-region replication, alternative to global tables. Scenario. You need to maintain a replica of a table in another AWS region, but perhaps with custom conflict resolution logic or for auditing purposes. Solution. A Lambda function triggered by the stream reads changes and writes them to a replica table in a different region. While global tables offer a fully managed solution for this, custom replication via streams gives you more control over the process. Auditing and compliance. Scenario. Your application needs to log every change made to sensitive data for compliance or auditing purposes. Solution. Stream all item modifications. A Lambda function processes these records and writes them to an audited log in Amazon S3 or a dedicated logging service, providing a granular, immutable history of changes. Cache invalidation. Scenario. You use an in-memory cache, like Amazon Elasticache, to speed up reads from your DynamoDB table. When an item in DynamoDB changes, the cached version becomes stale. Solution. A Lambda function triggered by the stream identifies the modified item and invalidates the corresponding entry in the cache, ensuring users always see fresh data. Notifications and messaging. Scenario. A new order is placed or a support ticket status changes. You want to notify users via email, SMS, or an in-app message. Solution. The stream triggers a Lambda function, which then sends data to Amazon SNS, Simple Notification Service, for fan-out messaging, or to Amazon SQS, Simple Queue Service, for asynchronous processing by other services, which then send the actual notifications. Data lake ingestion. Scenario: you want to capture all changes in your DynamoDB table and store them in a data lake, e.g., on Amazon S3, for long-term analytics and historical purposes. Solution: a Lambda function processes stream records and writes them as files, e.g., CSV, Parquet, to an S3 bucket in a structured way. Important considerations for using streams and triggers. Batching. Lambda functions typically process stream records in batches, not one by one. Your Lambda code needs to be designed to handle multiple records in a single invocation. Error handling and retries. If your Lambda function encounters an error while processing a batch, DynamoDB will retry sending the entire batch until it succeeds or the records expire after 24 hours. This means your Lambda function must be idempotent, capable of processing the same batch of records multiple times without causing unintended side effects, e.g., sending duplicate emails. Concurrency. You can configure the concurrency of your Lambda function processing the stream. Each shard of your DynamoDB stream has a dedicated Lambda invocation. Cost. You pay for read capacity from the stream, which is very low, and for your Lambda invocations and compute time. Stream view type strategy. Carefully choose your stream view type. Any WNDLD images provides the most context for complex logic, but consumes more storage and potentially more processing time in Lambda if you don't need all the data. Conclusion: building reactive applications. DynamoDB streams and triggers, via AWS Lambda, provide an incredibly versatile and powerful mechanism for building event-driven applications that react to changes in your data in real time. By decoupling data modifications from subsequent actions, you can build highly scalable, resilient, and flexible systems. This pattern helps unburden your primary application code from complex, real-time processing tasks, allowing it to focus on its core responsibilities. You've learned the power of making your applications reactive. Now, as your applications grow and handle immense loads, optimizing their performance and managing costs becomes paramount. In the next chapter, we will shift our focus to the crucial aspects of optimizing performance and cost: throughput, capacity, and hot partitions. We'll delve into how DynamoDB dimensions its capacity, how to choose between provisioned and on-demand modes, and how to troubleshoot and prevent performance bottlenecks like hot partitions, ensuring your application runs efficiently and affordably. Optimizing performance and cost, throughput, capacity, and hot partitions. You've designed your DynamoDB data model, you've mastered CRUD operations, and you've even leveraged the power of streams for real-time reactivity. Now, as your application grows, the twin concerns of performance and cost efficiency become paramount. DynamoDB's speed at any scale is its hallmark, but achieving it optimally requires a deep understanding of its capacity model. A poorly optimized DynamoDB table can quickly become a performance bottleneck or an unexpected drain on your AWS bill. This chapter delves into the practical aspects of managing your table's throughput, understanding capacity modes, and diagnosing common performance pitfalls like hot partitions. Understanding throughput. Read capacity units, RCUs, and write capacity units, WCUs. DynamoDB uses a unique capacity model based on read capacity units, RCUs, and write capacity units, WCUs. These units determine the rate at which your application can read from and write to your tables. Think of them as pre-purchased slots for database operations. Read capacity units, RCUs. One RCU provides one strongly consistent read per second for an item up to 4 KB in size. One RCU provides two eventually consistent reads per second for an item up to 4 KB in size. If your item is larger than 4 KB, it consumes more RCUs. For example, a 6 KB strongly consistent read consumes 2 RCUs because it exceeds 4 KB and falls into the 4 to 8 KB range. Query and scan operations consume RCUs based on the total size of the items read across the entire operation before any filter expressions are applied. Write capacity units, WCUs. One WCU provides 1 write per second for an item up to 1 KB in size. If your item is larger than 1 KB, it consumes more WCUs. For example, a 1.5 KB write consumes 2 WCUs. Conceptual example. If your application performs 10 strongly consistent reads per second, where each item is 3 KB, you would need 10 RCUs. 10 reads sec 1 RCU read equals 10 RCUs. If your application performs 20 eventually consistent reads per second, where each item is 5 KB, you would need 20 RCUs. 20 reads sec 2 RCUs read for 5 KB item equals 40 RCUs, but 2 reads per second per RCU for eventually consistent mode. So 42 equals 20 RCUs. If your application performs 5 writes per second, where each item is 0.5 KB, you would need 5 WCUs. If your application performs 5 writes per second, where each item is 1.5 KB, you would need 10 WCUs, because each write consumes 2 WCUs. Capacity modes, on-demand versus provisioned. DynamoDB offers 2 capacity modes, allowing you to choose how you manage your RCUs and WCUs, balancing cost and predictability. 1. On-demand capacity. How it works. With on-demand, you don't provision any capacity upfront. DynamoDB automatically scales up and down to accommodate your application's actual read and write throughput. You simply pay for the requests you make and the data you store. Benefits. Simplicity. No need to predict workloads or manage auto-scaling configurations. Cost-effective for unpredictable workloads. Ideal for applications with highly spiky, unpredictable, or infrequent traffic patterns. If your table is idle, you pay almost nothing for capacity. No throttling within limits. As long as your traffic doesn't exceed 2x your previous peak within 30 minutes or a certain baseline, your requests are generally not throttled due to exceeding capacity. When to use. New applications with unknown traffic patterns. Workloads that are highly sporadic or unpredictable. Development and test environments. Applications for which operational simplicity and avoiding throttling are more critical than minimizing every penny of cost. 2. Provisioned capacity. How it works. With provisioned capacity, you specify the number of RCUs and WCUs you expect your application to need. You pay for this provisioned capacity, whether you use it or not. DynamoDB then allocates this capacity to your table, guaranteeing that your application can perform operations up to those limits. Benefits. Cost-effective for predictable workloads. Often cheaper than on-demand if you have a stable, predictable workload that runs consistently. Guaranteed throughput. Provides a consistent performance baseline, as long as you account for potential hot partitions within that capacity. Disadvantages. Throttling. If your actual read or write requests exceed your provisioned capacity, DynamoDB will reject those requests, resulting in errors in your application, e.g., provision throughput exceeded exception. Management overhead. Requires you to monitor usage and adjust provisioned capacity manually or via auto-scaling. When to use. Applications with steady, predictable traffic patterns. Workloads where cost optimization for a consistent baseline is paramount, when you have finely tuned and well-understood access patterns. DynamoDB auto-scaling for provisioned capacity. Auto-scaling helps manage provisioned capacity by automatically adjusting your RCUs and WCUs based on predefined utilization targets. You set a minimum and maximum capacity, and DynamoDB, via AWS application auto-scaling, will scale up during peak times and scale down during quieter periods, helping you avoid throttling while still managing costs. This is often the best of both worlds for predictable but variable workloads. Optimizing capacity consumption, efficient data access. Regardless of your chosen capacity mode, optimizing how your application consumes RCUs and WCUs is key to both performance and cost efficiency. Prioritize getItem and query over scan. As discussed in Chapter 5, scan operations are notoriously inefficient. They read through every item in a table, regardless of whether a filter is applied, consuming significant RCUs. Always try to design your access patterns to use getItem for single-item lookups or query for retrieving data within a specific partition using the primary key or a GSI. If you must use scan, consider implementing parallel scans for large tables to distribute the load, or use filter expressions carefully. Optimize item sizes. DynamoDB charges based on 4 KB blocks for reads and 1 KB blocks for writes. Keep your items as small as possible. If you have large attributes, e.g., long text, images, consider storing them in Amazon S3 and putting only the S3 object key in your DynamoDB item. This is a common and highly effective pattern for managing large binaries. Use eventually consistent reads where possible. Eventually consistent reads consume half the RCUs of strongly consistent reads. For use cases where immediate data consistency is not critical, e.g., displaying a user profile that updates infrequently or non-critical analytics, eventually consistent reads are a great cost saver. Batch operations, batch get item, batch write item. These operations allow you to retrieve or write multiple items in a single request, reducing network round trips and improving overall efficiency, especially for many small items. Utilize indexes effectively and prudently. Secondary indexes provide flexibility but come with costs. Each GSI has its own RCUs WCUs. Every write to the base table also counts as a write to its associated GSIs. Project only the necessary attributes into your secondary indexes, keys only or include, to minimize storage and write costs. Projecting all attributes will copy the entire item into the index, and every write to the base table must update the full projected item in the index. Time to live, TTL. For data that naturally expires, e.g., session tokens, temporary logs, old sensor data, enable TTL on your table. DynamoDB automatically deletes expired items at no cost, which frees up valuable storage and avoids unnecessary query scan operations on stale data. Diagnosing and mitigating hot partitions. A hot partition is a single physical storage partition that is receiving a disproportionately high amount of read or write traffic compared to other partitions in your table. This can lead to throttling, even if your overall table capacity, RCU/WCU, seems sufficient. It's like one lane of a highway experiencing a massive traffic jam while other lanes are free-flowing. Symptoms of hot partitions. Throttling. Your CloudWatch metrics for read throttled events or write throttled events are high, even if consumed read capacity units or consumed write capacity units are far below your provisioned limits. Increased latency. Operations targeting the hot partition experience higher latencies. CloudWatch metrics. Monitor the consumed read capacity units and consumed write capacity units at the partition level, using detailed metrics in CloudWatch to identify which specific partition keys are receiving excessive traffic. Causes of hot partitions. Low cardinality partition key. Using a partition key with very few unique values, e.g., status equals active, directs all traffic to a handful of partitions. Non-uniform access patterns. Even with high cardinality, if a few specific partition key values receive the vast majority of traffic, e.g., a most popular product in an e-commerce store, or the current top trending topic in a social media app, those partitions become hot. Sequential or monotonically increasing partition keys. Using purely sequential IDs or timestamps as partition keys can cause all new writes to hit the same partition repeatedly, especially during high write bursts. DynamoDB's hashing algorithm works best with diverse, non-sequential inputs to distribute data evenly. Strategies to mitigate hot partitions. Review partition key design. This is the most crucial step. Increase cardinality. Choose partition keys with a very high number of unique values that are accessed uniformly. Utilize composite keys for distribution. If deviceid is your partition key and one device is very chatty, consider if adding a time component, e.g., device ID hash yimmdd, helps distribute that device's activity across daily partitions. Add randomness, advanced. For extremely high volume, uniform write workloads that are inherently concentrated on a few keys, e.g., logging activity for a single popular website, introduce artificial randomness to the partition key. For example, concatenate a random number, 1 to 100, or a hash prefix to the actual partition key. This spreads the writes across many logical partitions, which map to different physical partitions. You then parallel query these logical partitions when reading. This ensures even distribution across your logical partitions, but requires your application to manage the reading across these shards. Optimize read-write patterns. Avoid over-indexing. Every GSI adds to write costs and can exacerbate hot partition issues if its own key design is poor. Parallel scans. For analytical workloads, where scanning is unavoidable, utilize parallel scans to distribute the read load. Load balancing and retry logic. Implement robust retry and backoff logic in your application. If a request is throttled, the SDKs generally handle retries. For high-scale applications, consider client-side load balancing of requests across your partition key space. Leverage DynamoDB system features. Adaptive capacity. DynamoDB automatically attempts to rebalance partitions and adapt to uneven access patterns for tables using provisioned capacity. This generally works well for workloads with gradual shifts in access. On-demand capacity. As mentioned, on-demand mode largely handles hot partitions for you by dynamically scaling. While it can still be limited by the maximum throughput supported by a single partition, it automatically adjusts for most dynamic traffic. Monitoring your table's health. Amazon CloudWatch is your best friend for monitoring DynamoDB. Key metrics to watch include consumed read capacity units, consumed write capacity units, to understand your consumption. Read throttle events, write throttle events, to detect throttling. Latency for get item, put item, etc., to track performance. Returned item count, for understanding query scan results. By setting CloudWatch alarms on metrics like throttled events, you can be proactively notified of potential issues before they impact your users. Conclusion: mastering the art of DynamoDB operations. Optimizing DynamoDB for both performance and cost is an ongoing process, requiring a keen eye on your access patterns and thorough monitoring. You now understand the core concepts of RCUs and WCUs, the trade-offs between on-demand and provisioned capacity, and how to effectively leverage DynamoDB auto-scaling. Most importantly, you are equipped with strategies to prevent and mitigate hot partitions, the silent killer of DynamoDB performance. By applying these principles, you can ensure that your DynamoDB tables continue to deliver the promised speed at any scale, while keeping a tight rein on your cloud expenditures. However, a highly performing database is only as good as its security. In the next chapter, we will shift our focus to securing your DynamoDB applications. IAM best practices, exploring how to control access to your data, protect it from unauthorized users, and implement robust security measures at every layer of interaction. Securing your DynamoDB applications. IAM best practices. You've mastered data modeling, learned to interact with DynamoDB, adopted event-driven patterns, and even optimized for performance and cost. But all these capabilities are meaningless if your data isn't secure. Security is not an afterthought. It's a foundational pillar of any robust application. In the cloud, and particularly with a managed service like DynamoDB, much of the underlying infrastructure security is handled for you by Oz. This is part of the shared responsibility model, where AWS secures the security of the cloud. And you are responsible for security in the cloud, specifically, controlling access to your DynamoDB tables and protecting your data within them. This chapter focuses on securing your DynamoDB applications, primarily through AWS Identity and Access Management, IAM, and exploring DynamoDB's built-in encryption features. AWS Identity and Access Management, IAM, the gatekeeper. Oz IAM is the service that lets you securely control access to AWS resources. It's the central place where you define who can do what with your DynamoDB tables. In IAM, you work with IAM users, long-term identities for people or services. IAM roles, temporary identities that an entity, like a Lambda function, an EC2 instance, or even another AWS account, can assume to gain permissions. This is the preferred method for granting permissions to applications running on Oz. IAM groups, collections of IAM users, making it easier to manage permissions for multiple users. IAM policies, JSON documents that define permissions. They specify what actions are allowed or denied on which resources, and under what conditions. To secure your DynamoDB tables, you will predominantly use IAM policies. These policies can be attached to IAM users, roles, or groups, granting them specific permissions. Controlling access to DynamoDB tables. The fundamental way to control access to your DynamoDB tables is to explicitly allow or deny actions on them using IAM policies. The principle of least privilege. The golden rule of security is to grant the minimum permissions necessary for a user or application component to perform its tasks. Don't give a Lambda function permission to delete a table if it only needs to read from it. Don't grant DynamoDB all actions if only specific operations like putItem and getItem are required. Common DynamoDB actions in IAM policies. You'll typically specify DynamoDB actions prefixed with DynamoDB. Examples include DynamoDB, getItem, permission to read a single item. DynamoDB, putItem, permission to create or replace an item. DynamoDB, updateItem, permission to modify an item. DynamoDB, deleteItem, permission to delete an item. DynamoDB, query, permission to perform a query operation. DynamoDB, scan, permission to perform a scan operation. Resource-level actions like DynamoDB, create table, DynamoDB, update table, DynamoDB, delete table are typical for administrators. Applying policies. IAM policies specify the effect, allow, deny, action, the operations, and resource, the ARN of the table or index they apply to. Conceptual example of a policy. Imagine a policy conceptually saying, allow the getItem and query actions on the MyDataTable table and on any global secondary indexes associated with it. This policy would be attached to the IAM role that your application's Lambda function assumes. For instance, allowing it to retrieve and query data from that specific table. Fine-grained access control, FGAC. DynamoDB goes beyond simple table-level access permissions. It supports fine-grained access control, allowing you to define permissions at the item level and even at the attribute level within an item. This is incredibly powerful for multi-tenant applications or scenarios where different users have different data visibility. Fine-grained access control is achieved by adding conditions to your IAM policies that check attributes of the item being accessed. One item-level access control, you can restrict access to specific items based on their primary key values. Conceptual example, allow getItem and updateItem on the user's table only if the user ID of the item being accessed matches the user ID of the currently authenticated user. This is commonly done using IAM policy conditions that refer to a special DynamoDB key called DynamoDB leading keys. This ensures a user can only interact with their own data when the primary key contains their ID2 attribute-level access control. You can control which individual attributes within an item an IAM principal can read or write. Conceptual example, allow an application to put item into the user profiles table, but prevent it from writing to the asadmin or salary attributes. This is achieved using other DynamoDB-specific condition keys. DynamoDB attributes, for controlling access to specific attributes when performing actions like putItem, updateItem, getItem, query. DynamoDB select, for controlling which attributes can be returned as part of a query or scan operation. DynamoDB return values, for controlling which attributes are returned by write operations. FGAC provides powerful control, but it also adds complexity to policy management. Always test your fine-grained policies thoroughly. Encryption, protecting your data. DynamoDB offers robust encryption capabilities to protect your data both when it's stored at rest and when it's moving across networks in transit. 1. Encryption at rest. All user data stored in DynamoDB is encrypted by default. You have a choice of encryption keys. AWS-owned key, default. This is the default encryption option. Oz manages the encryption key on your behalf, and you don't incur any additional costs for it. It's a great baseline for security. Oz Managed Key, KMS. You can choose to have your table encrypted with an AWS Key Management Service, KMS, key that is managed by Oz in your account. This gives you more control and auditability over the key usage, as all KMS API calls are logged in AWS CloudTrail. Customer Managed Key, KMS CMK. For the highest level of control and auditability, you can provide your own KMS Customer Managed Key, CMK. This allows you to manage the key's lifecycle, grant permissions, and have full control over its use. This is often required for compliance with specific regulatory standards. All encryption at rest is transparent. Your application code doesn't need to do anything special to encrypt or decrypt data. DynamoDB handles it automatically. 2. Encryption in transit. Whenever data is sent between your application and DynamoDB, it is encrypted using Transport Layer Security, TLS, also known as SSL. This is enforced for all DynamoDB API endpoints, ensuring that data is protected from eavesdropping or tampering as it travels over the internet. You don't need to configure anything for this. It's automatically handled by Oz, securing application access to DynamoDB. A common mistake is embedding Oz credentials, like access keys and secret keys, directly into application code. This is a severe security risk. The preferred and most secure method for your applications to access DynamoDB is through IAM roles. How IAM roles work for applications. You create an IAM role and attach an IAM policy to it that grants the necessary DynamoDB permissions. Your Oz compute resource, e.g., an EC2 instance, an AWS Lambda function, an ECS task, an EKS pod, is configured to assume this IAM role. When your application code runs on that resource, it automatically retrieves temporary security credentials from the AWS metadata service. These credentials have the permissions defined by the assumed IAM role. The Oz SDKs in your application automatically handle the credential fetching and refresh process. This approach eliminates the need to manage long-lived credentials in your application code, significantly reducing the risk of accidental exposure or compromise. Common security anti-patterns to avoid. Overly permissive IAM policies. Using for actions, e.g. DynamoDB, or resources, e.g. ARN Oz DynamoDB, is a critical anti-pattern. Always specify the minimum necessary actions and target resources. Hard-coding credentials. Never embed Oz access keys and secret keys directly into your application code, configuration files, or version control repositories. Use IAM roles or environment variables for credentials. Ignoring encryption. While DynamoDB encrypts at rest by default, ensure you understand the key management options and choose the one that meets your compliance and control requirements. No monitoring. Without proper monitoring, you won't know if your security boundaries are being tested or breached. Oz CloudTrail logs all API calls to your Oz account, including DynamoDB operations, essential for auditing. Amazon CloudWatch monitors DynamoDB metrics and can alert on unusual activity or errors. AWS Config can track configuration changes to your DynamoDB tables, helping detect accidental or malicious changes. Lack of network segmentation. While DynamoDB is a managed service, ensure your applications accessing it are running in secure networks, e.g., private subnets within a virtual private cloud, VPC, to minimize exposure. Conclusion: security as a continuous practice. Securing your DynamoDB applications is a continuous process that involves careful planning, adherence to the principle of least privilege, and diligent monitoring. By leveraging AWS IAM for fine-grained access control, utilizing DynamoDB's robust encryption features, and adopting secure practices like using IAM roles for applications, you can build highly secure and compliant solutions. You've now covered how DynamoDB functions, how to model data, interact with it programmatically, make applications reactive, optimize performance, and secure your data. The final piece of the operational puzzle is ensuring the ongoing health of your database. In our next chapter, we will shift our focus to monitoring, troubleshooting, and maintenance, equipping you with the tools and techniques to keep your DynamoDB applications running smoothly and efficiently in production. Monitoring, troubleshooting, and maintenance. You've built a robust DynamoDB application, capable of scaling to meet any demand. But deploying an application into production is just the beginning. The real work then shifts to ensuring its continuous health, performance, and reliability. This involves a crucial triumvirate: monitoring its vital signs, troubleshooting issues when they arise, and performing routine maintenance to keep it running smoothly. Ignoring these aspects is like buying a high-performance sports car and never changing its oil or checking its tires. Eventually, it will break down. For critical business applications, such breakdowns can lead to lost revenue, frustrated users, and damaged reputation. This chapter will equip you with the tools and best practices to keep your DynamoDB applications healthy and performant. Monitoring your DynamoDB tables. The vital signs. Effective monitoring is about gaining visibility into your table's operational health and performance. It allows you to detect issues early, often before they impact your users, and understand trends that inform future capacity planning. 1. Amazon CloudWatch, your central monitoring hub. Amazon CloudWatch is the primary monitoring and observability service for AWS resources, including DynamoDB. It collects an array of metrics that provide deep insights into your table's behavior. Key metrics to monitor: capacity usage, consumed read capacity units, how many RCUs your table is actually consuming; consumed write capacity units, how many WCUs your table is actually consuming. Comparing these to your provisioned read capacity units and provisioned write capacity units, if using provisioned mode helps determine if you're over or under provisioned. Throttling events. Read throttled events indicates when read requests are being rejected because they exceed your provisioned or on-demand capacity limit. This is a critical metric to watch for. Write throttled events indicates when write requests are being rejected. Latency. Successful request latency, the average time taken for successful requests, e.g., get item, put item, query. High latency can indicate performance bottlenecks. System errors. System errors indicates internal DynamoDB errors that can affect your table. While rare, they are important to track. Global table metrics. For global tables, you'll also monitor replication lag, replication latency, to ensure data is synchronizing quickly across regions. Setting CloudWatch alarms. Metrics are useful, but you need to be notified when something goes wrong. CloudWatch alarms allow you to set thresholds for specific metrics. For example, you can configure an alarm to notify you via email, SMS, or an Oz SNS topic that can trigger other actions. If read throttled events or write throttled events exceed 0 for a sustained period. Successful request latency for a critical operation goes above a certain threshold, e.g., 50 milliseconds for several consecutive minutes. Consumed capacity reaches a high percentage, e.g., 80% of provisioned capacity, indicating you might need to scale up soon. 2. Amazon CloudWatch logs. While CloudWatch metrics track events, CloudWatch logs is where you store, monitor, and analyze log data. Your application's logs, e.g., from AWS Lambda functions or EC2 instances that interact with DynamoDB, should be ingested into CloudWatch logs. This allows you to debug application errors. When your application experiences an error interacting with DynamoDB, e.g., conditional check failed exception, the detailed error messages and stack traces in your application logs are invaluable for diagnosis. Auditing, combined with AWS CloudTrail, which logs all API calls made against your Oz resources, including DynamoDB. CloudWatch logs helps provide an audit trail of who did what and when. 3. AWS X-Ray, distributed tracing. In modern distributed applications, a single user request might traverse multiple services, hitting an API gateway, invoking a Lambda function, then querying a DynamoDB table, and perhaps interacting with another service. Oz X-Ray helps you visualize this entire request flow. Trace map. X-Ray generates a service map showing all the interconnected services involved in a request. Performance bottlenecks. It highlights potential bottlenecks, showing you exactly how much time a request spent in DynamoDB versus other services, helping pinpoint the source of latency. Error diagnosis. X-ray helps correlate errors across services for faster troubleshooting. While your application code needs to be instrumented to send traces to X-ray, it provides a powerful holistic view when debugging complex interactions involving DynamoDB. Troubleshooting common DynamoDB issues. Despite all efforts, issues can arise. Here's how to approach common DynamoDB problems: throttling, diagnosis. High read throttled events or write throttled events in CloudWatch. If using provisioned capacity, check if consumed capacity units are hitting your provisioned limits. Root cause often indicates insufficient capacity or, more commonly, a hot partition. Use CloudWatch's detailed metrics by particular partition key, where available, e.g., for DynamoDB Accelerator DAX or application logging to identify the hot partition key values. Resolution, on demand, wait for DynamoDB to scale. If persistent, consider your access patterns. Provisioned, increase provisioned capacity manually or via auto-scaling. Hot partitions, this is a data modeling issue. Revisit your primary key design, Chapter 3, and data modeling patterns, Chapter 6, to ensure even distribution. Consider techniques like adding randomness or using GSIs to offload problematic access patterns. High latency. Diagnosis. High successful request latency for specific operations, e.g. getItem. Root cause can be network issues, large item sizes, cold starts for the compute interacting with DynamoDB, e.g. Lambda cold starts, or even ongoing throttling that isn't fully rejecting requests but slowing them down. For GSI queries, high latency could also indicate eventual consistency lag if your application is querying very recent writes. Resolution. Use X-ray to pinpoint where the latency is introduced. Optimize item sizes. Review network configuration. For GSIs, understand eventual consistency. Application errors, e.g., conditional check failed exception, diagnosis. These errors typically appear in your application logs. Root cause, your application is attempting an operation with a condition that is not being met, e.g., trying to put item if not exists. But the item already exists, or update item if balance 0, but balance is 0. Resolution, analyze your application logic. Is the condition expression correct? Is there a race condition where another process modified the item just before your operation? Design for idempotency and handle these exceptions gracefully in your code. Connectivity issues, diagnosis. Your application logs show network timeouts or connection refused errors when trying to reach DynamoDB. Root cause, network configuration issues, e.g., incorrect VPC endpoint settings for DynamoDB, security group NACLS blocking traffic, DNS resolution problems. Resolution, verify your network configurations, especially if using a VPC endpoint for DynamoDB. Ensure your application has outbound access to DynamoDB, which is a public service, though you can use VPC endpoints for private network access. Maintenance best practices, proactive health management. Regular maintenance ensures data integrity, compliance, and cost-effectiveness. Backup and restore strategy, point-in-time recovery, PITR. This is a critical feature. When enabled, DynamoDB continuously backs up your table data, allowing you to restore it to any point in time within the last 35 days, up to the second. It's always on once enabled and transparently integrated. Always enable PITR for your critical production tables. On-demand backup. For specific recovery points, e.g., before a major deployment or data migration, you can also create manual, full backups of your table. These are stored until you explicitly delete them and do not expire after 35 days. Restore. If data is corrupted or accidentally deleted, you can restore a new table from a PITR backup or an on-demand backup. It creates a new table. It does not overwrite the existing one. Why both? PITR is for operational recovery from accidental deletion or corruption. On-demand is for specific archival snapshots or for data transfer tasks. Data lifecycle management, time to live TTL. For data that naturally expires, e.g., user sessions, temporary notifications, old logs, configure TTL on your table. DynamoDB automatically deletes expired items at no cost to you. This reduces storage footprint, improves query performance by keeping tables lean, and potentially saves on capacity. Capacity planning review. Regularly review your CloudWatch consumed capacity units metrics, especially if using provisioned capacity. Are you consistently underutilizing or overutilizing your provisioned throughput? Adjust your capacity or auto-scaling settings based on actual usage trends. Secondary index management. As your access patterns evolve, some secondary indexes might become redundant or inefficient. Periodically review your LSIs and GSIs. Removing unused indexes can save on storage costs and write capacity. Adding new indexes might be necessary to support new application features efficiently. Security audits. Regularly review your IAM policies for DynamoDB, Chapter 10. Ensure they adhere to the principle of least privilege. Check AWS CloudTrail logs for any suspicious API activity related to your DynamoDB tables. Data archival and export. For very old or infrequently accessed data, consider archiving it to more cost-effective storage like Amazon S3. DynamoDB streams, Chapter 8, can be used to capture data changes for ingestion into a data lake S3 or data warehouse for long-term storage and analytical purposes. Conclusion: continuous operational excellence. Monitoring, troubleshooting, and maintenance are not glamorous, but they are absolutely essential for the long-term success of any application relying on DynamoDB. By proactively monitoring your table's metrics, understanding how to diagnose common issues, and implementing robust backup and data lifecycle strategies, you transform reactive firefighting into proactive health management. You gain confidence not just in building scalable applications, but in operating them reliably and cost-effectively in production. You've now learned the technical capabilities of DynamoDB and the operational best practices. In the final chapter, we'll shift to a broader perspective, bringing it all together by exploring real-world architectures and best practices, a developer's toolkit. We'll examine how DynamoDB integrates into larger AWS ecosystems, review common application patterns, and consolidate the key takeaways to provide you with a comprehensive developer's checklist for successful DynamoDB adoption. Real-world architectures and best practices, a developer's toolkit. Congratulations! You've journeyed through the core concepts of DynamoDB, mastered its fundamental operations, delved into advanced data modeling, explored transactional capabilities and global distribution, harnessed the power of event-driven architectures, optimized for performance and cost, and learned the critical aspects of security, monitoring, and maintenance. You now possess a comprehensive understanding of Amazon DynamoDB from a developer's perspective. In this final chapter, we'll synthesize all this knowledge by looking at DynamoDB in the context of real-world multi-service architectures. We'll examine common patterns, integration points with other OS services, and consolidate the most vital best practices and anti-patterns to avoid into a practical developer's toolkit. This chapter is designed to serve as a high-level guide for applying your new expertise effectively. DynamoDB in the broader AWS ecosystem. DynamoDB rarely operates in isolation. Its power is amplified when combined with other OS services in a well-architected solution. Here are some common integration patterns: serverless API, API Gateway plus Lambda plus DynamoDB. Pattern. This is perhaps the most common and powerful pattern for web and mobile backends. An Amazon API Gateway endpoint receives HTTP requests, which trigger AWS Lambda functions. These Lambda functions then perform CRUD operations on DynamoDB based on the request. Benefits: fully managed, highly scalable, paper execution, and no servers to provision or manage. DynamoDB handles the data persistence at scale, while Lambda handles the compute logic. Example: a REST API for a to-do list application where GET tasks triggers a Lambda to query DynamoDB, and post tasks triggers a Lambda to put item. Real-time data processing, DynamoDB streams plus Lambda. Pattern: as discussed in Chapter 8, DynamoDB streams capture changes to your data, which then trigger OS Lambda functions. Benefits: enables real-time analytics, search indexing e.g. to Amazon OpenSearch Service, cache invalidation, cross-service data synchronization, and data archival to Amazon S3. Highly decoupled and event-driven. Example: a user activity table stream triggers a Lambda function that pushes data to an analytics pipeline or updates an aggregated user score in another DynamoDB table. Data lake and analytics, DynamoDB plus Kinesis, S3 plus Athena/Redshift. Pattern: data from DynamoDB can be exported or streamed into a data lake on Amazon S3 for long-term storage, complex analytics, or integration with other data sources. Benefits: allows you to leverage the analytical power of services like Amazon Athena for ad hoc SQL queries on S3 data or Amazon Redshift data warehouse without impacting your operational DynamoDB performance. Example: DynamoDB streams could be processed by a Lambda function that lands raw data in S3. Or use OzGlue to directly export DynamoDB tables to S3. Backend for WebMobile, DynamoDB plus AWS AppSync. Pattern: AWS AppSync is a managed GraphQL service. It can use DynamoDB as a data source, making it easy to build flexible and real-time APIs for modern web and mobile clients. Benefits: developers write less backend code. AppSync handles the GraphQL parsing, resolution, and real-time updates. Great for applications requiring complex data relationships or real-time subscriptions, leveraging DynamoDB's speed. Example: an application backend where users can subscribe to real-time updates for their favorite products or chat rooms powered by DynamoDB. Caching, DynamoDB plus Amazon ElastiCache. Pattern: while DynamoDB is fast, for extremely high read volumes on frequently accessed, unchanging data, you can place a cache, like Amazon ElastiCache, using Redis or Memcached in front of DynamoDB. Benefits: reduces the load on DynamoDB, further lowers read latency, and can reduce RCU consumption. Example: a product catalog where popular product details are cached. Updates to DynamoDB via streams plus Lambda could then invalidate the cache. Core best practices, your developer's checklist. Let's consolidate the most important lessons learned into a practical checklist for building with DynamoDB. 1. Embrace the access patterns first mindset. Before writing any code, list all the ways your application needs to query and update its data. This drives your primary key and secondary index design. Normalize your data like a relational database or design a schema without considering how you'll retrieve the data. 2. Master primary key design. Choose partition keys that ensure even data distribution and prevent hot spots. Use composite keys to enable efficient range queries on sorted data. Use low cardinality attributes, e.g., status equals active, or strictly sequential values as partition keys. 3. Leverage secondary indexes wisely. Use global secondary indexes, GSIs, for alternative access patterns that don't involve the main table's partition key. Use local secondary indexes, LSIs, for alternative sort orders within the same partition where strong consistency is required. Project all attributes into an index unless absolutely necessary, as it increases storage and write costs. Avoid creating excessive indexes, as each adds write cost. 4. Think single table design strategically. Consider combining multiple entity types into a single table using generic PK/SK attributes with prefixes. This simplifies operations and improves performance by co-locating data for common access patterns. Force single table design where it doesn't make sense, e.g., for very disparate entity types with no shared access patterns, or when it overcomplicates queries for simple use cases. 5. Denormalize judiciously. Duplicate data or embed related items where it improves read performance and avoids multiple round trips or complex application-side joins. Over-denormalize to the point where data consistency becomes impossible to manage or updates become overly complex costly. 6. Optimize for latency and cost. Prefer getItem and query over scan. Use batch getItem and batch writeItem for efficiency. Use eventually consistent reads whenever possible. They're half the cost of strongly consistent reads. Store large binaries in S3 with references in DynamoDB items. Do. Enable TTL for ephemeral data. Perform full scans on large tables in production applications unless it's for an administrative task. 7. Choose capacity mode wisely. Do. Use on-demand capacity for new, unpredictable, or highly spiky workloads. Do. Use provisioned capacity with auto-scaling for stable, predictable workloads to optimize cost. Over-provision capacity, just in case, or under-provision and face constant throttling. 8. Build for security. Do. Adhere to the principle of least privilege using IAM policies. Grant only the necessary DynamoDB actions on specific table arns. Do. Use IAM roles for applications running on AWS Compute, Lambda, EC2, ECS, etc. Never hardcode credentials. Do. Understand and leverage default encryption at rest and choose KMS encryption where appropriate for compliance control. 9. Embrace event-driven architectures. Do. Utilize DynamoDB streams with AWS Lambda to react to data changes in real time. Building decoupled, scalable workflows for tasks like indexing, notifications, or analytics. Over-rely on Lambda functions for complex, stateful, or long-running processes that are better suited for other services. 10. Monitor and maintain diligently. Do. Enable point-in-time recovery, PITR, for all critical tables. Do. Monitor key CloudWatch metrics, throttled events, latency, consumed capacity. Set up alarms. Do. Have a clear strategy for archiving old data. Let your tables run unmonitored or assume that, because it's a managed service, it requires no operational oversight. Common anti-patterns to avoid. Beyond the positive best practices, it's equally important to be aware of what not to do. Many common DynamoDB pitfalls stem from trying to apply relational thinking directly to a NoSQL database. Misusing scan operations. As previously emphasized, scan is often the most significant anti-pattern for performance-critical applications on large tables. Modeling for joins. Attempting to achieve joins at the application layer by making multiple getItem or query calls for related data. This leads to increased latency, complexity, and RCU consumption. Denormalize or use single-table design instead. Inefficient primary key design. Leading to hot partitions, this is a fundamental design flaw that undermines scalability and performance. Over-reliance on attribute-level filtering. Using filter expressions on query or scan operations is inefficient, as the filtering happens after capacity is consumed and data is read. Design your indexes so that most filtering happens on key attributes, key condition expression. Storing large items. Items much larger than a few hundred kilobytes become inefficient and costly. Link to S3 instead. Ignoring cost implications. Not understanding RCUs, WCUs, using provisioned mode for spiky workloads, or over-indexing can lead to unexpectedly high bills. Your DynamoDB journey continues. Mastering DynamoDB is a journey. It requires a shift in mindset, particularly for those accustomed to relational databases. It demands a deep understanding of your application's access patterns and a willingness to embrace denormalization and creative key design. The concepts and patterns covered in this book provide you with a robust toolkit to build highly scalable, performant, and resilient applications. You've gained an understanding that goes beyond surface-level API calls, delving into the architectural and operational considerations that truly unlock DynamoDB's full potential. As AWS constantly innovates, so too will DynamoDB continue to evolve. Stay curious, keep building, experiment, and remember that the best way to learn is by doing. Happy coding, and may your DynamoDB tables always remain performant, cost-efficient, and secure.